So welcome back again. We're pleased to announce the talk of Dr. Kranzlmueller. He's director of the Leibniz Computing Center, very active in the field of visualization. He's also professor of computational science at LMU Munich and one of the PIs of NOMAD. And his talk's going to be about scientific and information visualization. So, thanks for coming.
Thank you for the nice introduction. And if I press the right button, you should hear even more noise from me. Okay. So this talk is not about noise, it's about visualization. And as was mentioned, what you see up here is the Leibniz Supercomputing Center of the Bavarian Academy of Sciences and Humanities. And we are usually well known for doing supercomputing. We have one of the national HPC machines. We have SuperMUC, which used to be the fastest machine in Europe for a couple of weeks, and the fourth fastest machine on the planet. And right at this moment, we are actually in discussion negotiations with getting the next big machine, which is called SuperMUC Next Generation for the Star Trek friends. The question is, of course, why are we doing visualization? And at the end of the talk, I will get back to that question and also provide you with some insights. What I wanted to say here is basically, whatever we do with computing, we don't do just for the computing. We do it because we want to generate insights and we want to understand what's going on from a physics point of view, from the natural sciences point of view. It's not the computing. The computing is just a service. And as such, we also believe that the visualization is a service which we want to kind of obtain in order to gain insight and in order to understand what is actually going on. And we'll get to that in more detail. Actually, I was asked to provide an overview of possibilities and challenges. And to tell the truth, we could spend all week just discussing possibilities and challenges of visualization. So what I did is really extract a little part from my personal view with some ideas on where this goes to. And I should also mention a couple of people, so that the presentation was prepared mostly by Thomas Odaka, one of the members of the team. There are some slides which came from Jutta Dreher, and there is also Ruben Garcia in the room. Of course, you will see his name mentioned on one slide or the other where he provided some actual input. So Ruben is one member of the team who actually does what I'm trying to summarize here. So let us start with a little example. I give you one thing, the first visualization I did, and which was actually looking this way. And from what you see here, I'm sure you have no idea what it could be. Well, actually, when I was studying, I was also earning the money for my studies by working in a company. And the company was doing gears, gearboxes, these kinds of things. Actually, not the ones that you know in your car, but we did some that come up to 35 tons, so it's a little bit bigger. We did, for instance, if you've been in Budapest and you went up the hill, when it was broken, we went there to repair it. And what we see here is one of these gear wheels. Of course, you have no idea how big it is, because the dimension basically is missing here. You don't even see the teeth. Actually, this is for the person producing the wheel, the teeth. So what we did at that point, and that was part of my diploma thesis back in 1990 around, we basically produced this one automatically from the simulation. So what we did is we calculated whether the gear, how much power is on the gear, how it would fit together, and then they wanted to produce the concrete gear with pictures for the guys producing them. So it was not a person handwriting them, but it was automatically done from the simulation. Nothing has changed. It's still the same. It's going on today. At that point in time, what we had to do is we had to draw a line from here to here. We had to do our own coordinate system. And of course, we had other views of the same wheel, which basically looked like this, because we couldn't draw the teeth, so to say. That was not possible with the computational power we had today. Now, of course, if we go 1990, almost 30 years ago, if you would take your mobile phone here, for instance, that would be in 1990, that would be among the 100 fastest machines on the planet, so to say. So this is what we also see, when we take a look in visualization, and what do we have to take into consideration. So what you see here basically is a talk about visualization and how we could do it, with some partially philosophical questions to be answered, but also with many examples that my staff members did, that we did in the course of time, that should kind of bridge and give you some idea of where the problems are. The idea, as I said, is we want to create a visualized representation of whatever complexity the data set has. And the complexity is, of course, the point where it becomes crucial. What you're doing is you want to visualize materials. And of course you want to visualize them because you see something here, but that's not what you're interested. You want to go down to a level which you cannot usually see. So what we want to do is we want to take this complex data set and we want to make them easily understandable, so that a person looking at the data has an idea. Now the important point here is the person that comes into play. It's the person in the loop. And the person in the loop has a number of roles. First of all, you see something different than from what I do. You like different colors from what I like, for instance, yeah? The colors may have different meanings. And we often enough had people say, we want that in red. And the other one, why is that red? That should be yellow or something, yeah? So the person comes into play when it needs to become understandable. And we also see the person needs to interact with what we are seeing. So we're getting to that. The point that most students forget is when we talk about visualization, we talk about computer graphics. And computer graphics, and Ruben can confirm, is to a large extent mathematics, matrix transformations, matrix multiplications, these kind of things. Many students forget that the picture in the end is just a result. But in order to get there, you need to do lots of mathematics, these kinds of things. And then, of course, you use it in different fields. So you see architecture is a well-known example. All these figures that you have seen from the Berlin airport, for instance, they are just artificial pictures. Or from Stuttgart 21, just to name a few examples. Yeah? Geophysics, we will have some more. Material sciences is mentioned here, of course. And there is lots of things all going on in arts, medicine, metrology, these kinds of things. I would always say there are a couple of things where visualization helps when you see things that you cannot see in reality. So the realistic pictures is one group of pictures, but it becomes interesting when something is too small, something is too big, or something is even dangerous. So one of the things we did, for instance, was a training simulator for refineries, oil, petrol refineries, which was exploding, which sounds like a nice computer game, but of course you wouldn't do that training in reality. You would more or less try to see what you can do in this area. Here are a couple of examples which I wanted to show you. The first one is one of these architectural examples up there. You see a number of university buildings at the University of Linz in Austria, and they basically put this up because people were frightened that these large buildings would destroy their view at these kinds of things. Similar example in Stuttgart, when they built a dam in the mountains, they basically took the people into the room and showed them how this dam would look from their own garden, so they could get a feeling. And most people thought, oh, I don't even see that thing that we have been protesting against. Yeah? Typical example here, and that's what I said, most well-known, of course. Here is another example which goes a little bit more into things we don't see. This is actually from Hans-Peter Bunge. That's the visualization of the tectonic plate movement. So we know that our tectonic plates are moving, We don't know why exactly the way that they are doing it. So what he is visualizing here is temperature and pressure differences in the mantle of the Earth. Here is an example from culture, preserving cultural objects. What we see here are objects from Bavaria, which are very expensive and which get destroyed if they come in contact with air and light. So what we do is we do high-resolution scans, and then we can show them to the people again, and in order to kind of keep the quality for a long time. We can, of course, also manipulate that. We have these terracotta warriors that you have seen on television. We have one of them scanned, and the archaeologists restored them to the original coloring, which, interesting enough, they had green color. In that case, it was a green warrior, yeah? Which you cannot see anymore because the environment has already destroyed the object. And then that goes on with different things. Here's one example from climate. This is actually, or climate and weather, it's actually a flooding simulation. What you see here is the Mediterranean, Italy here, you see Genoa here, and this is a flooding that happened twice. Once in 2011 and 2014, Genoa was flooded, and by funny coincidence, we had a European Union-sponsored project from 2011 to 2014. So we studied the flooding here, and we had actually a review going on where they could see this flooding. And once the reviewer could understand what happens here in the clouds, we could show them the clouds and the accumulation of clouds over a certain small area. And that just looked already dangerous from that point of view. Simply by showing them the pictures, they could understand what was going on and why it was just hitting one area of Genoa at that point in time. So we need it basically in order to gain understanding. And the sentence, the picture's worth more than 1,000 words, I think everybody knows. Here's another example, and I promised you some examples. Here's an example which we did with Professor Zhou Ren Wu from Taiwan. And they had an interesting phenomenon there. They had the typhoon coming in, and when the typhoon was through, the bridge broke down. They didn't understand what was going on. So what he did was basically study the pillars of the bridge, what you see here. And actually what happened, the typhoon comes in on top of the landscape, of course. But the waves kind of were digging out the bridge. So it was a simple example where we could easily show with the simulation to everybody, even, sorry for the joke, even the politicians understand that the bridge was breaking down if you removed the ground from there. Yeah? That was an easy thing. So they did that, and they used visualization for that particular case. So we know that scientific data can be incredibly complex, and of course we're going up to terabytes of data. Whatever you do with your data, visualization is growing. One of the main problems, and again Ruben can confirm, is that the data is growing immensely. Even if your phone gets more powerful, the data that we want to visualize is more than you can store on your phone. I've said that before, and of course that also means in order to get access to the data, one of the things we always have to do is we also need to make sure that there's a good network connection to the machine producing it. It doesn't help that you have SuperMOOC or another HPC machine in the room. You also need to make sure that you get the data as quickly as possible over to the other side. And we also have inside the machine the problem that the bus is the limiting factor. How much can we get over there? And once we have that, we believe we can show things that we haven't seen before. But of course, as I mentioned with the terracotta warriors, we can also change that. We can also add certain viewpoints that we want to see. We want to go in there interactively. You want to change, you want to see more blue when you inspect the bridge. Or you want to use different input devices. If you work in 3D, is that the appropriate input device? Or would you want to use something different to navigate there? You would also kind of want to have yourself studying the data. How would you look in? You would like to zoom into an area. You would like to find out that you're only interested in a selection of the data. I think you mentioned that just over coffee. Yeah? They were kind of using data that was produced by sensors, but there's always a calibration area and there's also a fade-out area. Yeah? You would like to discard that. You want to look at the stuff that is really interesting. And of course, you would like to manipulate. So one thing that we did, an interesting project, was we wanted to manipulate data while it is being simulated and visualize it on the other side. Sounds trivial, but of course, if you have that amount of data that you are dealing at this point in time, well, just a simple manipulation generates huge amounts of data and then needs to get back to the machine. So you need these high frame rates, which means you need enough frames, enough pictures, so to say, being produced in order to still make that interactive. And of course, you need to process the user input. And users, well, we try to understand, we try to predict what they are doing when they are inside. And the best example is if you go to one of these amusement parks. Yeah? If you go to Disney studios, Disney worlds or whatever, they always try to predict where people would be navigating. They try to make a path that is interesting, because otherwise there is no data. But of course, it's something different when you are working in science. Yeah? You want to study explicitly some things that you might not have thought about before. So if we take a closer look, we could also distinguish between things that are somehow real, even if we can see them, and some things that come in just from the information we want to add on that. I always take an example. You could, for instance, draw a graph of people using Facebook. And if you do that, you see very nicely that usually on all the continents, you see the people on the border of the continents. Here you have the shape of the continents by just adding information which has nothing to do with geography. Just people interacting on a certain social media. We distinguish these two things just also kind of to help us about the methodology we're using in both areas. So scientific visualization is something natural in terms of the data that we are doing, and something that things, as I said, that we have seen before. And information visualization, where we enhance the display, where we add things that we want to additional put in onto the data, which additional information is being shown to us in order to give us some more sight. Here's an example for scientific visualization. Again, a picture here. You see one of the mountains in the Alps. I think they told me actually which mountain is it. Sorry, I forgot. But the question here was, of course, what is happening to the glaciers? Now, the people working in that area have measured the glacier for years. And they knew that it was going back every year for a certain amount of meters. But they had only their numbers, their measurements. They had pictures, photographs, yeah? But what you can do here is basically we can overlay all the data from the last 50 years, and we can actually show how rapidly it is going back. So it's again something where the scientists wouldn't need it in that case, but the politicians need to understand what's going on, yeah? So it's a different group of people with a different background, but it can only be done by another group that has all the knowledge. So we create a natural representation, and what is the most difficult thing here? The most difficult thing here is not the mountain. The most difficult thing is how can you make snow look realistic? That's really the challenge here. We had to play quite a bit to that. We want to kind of help more with the understanding, again, at this point. So it's all natural here. Now the other point is this is all natural too. But this is not something that you would see anywhere. Yeah? You can go to the glaciers, you see something there. This is what Ruben was also working on in some of the projects. And what we wanted to do here is we wanted to use chain data, genomic data, and do some comparison between the different areas. So what you see here are gene sequences, and you see they are kind of shown in a room with, reality is it's 5 sides. So you have additional dimensions, and what you want to do is you want to compare these gene sequences. And you see some lines between different areas, and these lines indicate how the different areas, the different parts of the genome are kind of connected together. So you put something artificial in because you want to know about the relation between the objects, not the actual view of what the objects would look like. And of course, I mean, that was just some examples. Now the question was, which tools could you use? Now you want to use that for your own research. Which tools would you use? Well, and the answer to that one is always whenever we have a discussion with one of the customers, so to say, one of the scientists coming to us say, we want to use that. It depends. The question is always, it depends. It depends on the data that you have. It starts from the data format. How can we read in the data? How can we make sure that we understand what is in the data? It depends on what you want to do with the data. So what would you expect from the visualization? So it doesn't help if you go there and say, I want to visualize this data. You also need to kind of put up an expectation, a goal of what you want to achieve with it. So whatever scenario you have, you need different kinds of visualization techniques. And of course there is some, like volume rendering, is usually used for medical imaging. If you have your computer tomography, if you have your data, and whenever I have to do one of these things, I always go there and ask for getting a copy of my own data, just to see if we can visualize it. And you have different kinds of approaches you need there. And these software tools try to make visualization easier. And of course, they come with a purpose. So if you have a software tool that usually works for BMW to visualize the next car, it's something different than from where you want to visualize your material sciences. Yeah? And there's also the time component. If we take a student working on one visualization, then over time technology improves. We change graphics cards, we change the display, and the old visualization tool doesn't work anymore. So what we have here is just three of the most commonly used tools, or most commonly used tools in some of the areas. Let's say these are tools that people in the HPC community in Germany approach, and I would even say that this is kind of the major tools that we see here: Amira, Covise, and ParaView. So Amira is called a 3D visualization and analysis software for scientific data. We have modular software development included, and then we can do our own things. The emphasis here is on life sciences and material science. So this might be something you want to take a closer look at, but is also used as a general purpose tool. Again, with the restriction that it was first kind of intended for this particular area. You have some other features there, like stereoscopic rendering. I didn't mention that so far. But for us, it's also very important to have a 3D display and stereoscopic view on the data so that you see the distances more easily than what you have on a 2D display. Multi-display environments is what you saw with the gene sequence stuff, where we had a room for the visualization. And you should also check if it's a commercial product or not. So from experience, when we did our visualization center 5 years ago, we invested quite some amount in products, in real commercial tools, because our users were asking for them. One of them was the example, RTT, that we used that because BMW is using it. Now, meanwhile, we changed everything to our own open source and Linux compatible visualization tools, because we have more possibilities to adapt it to our needs. So the examples that you have seen is a mixture of all these tools. You have to take that into consideration because the tool evolves, the graphics, the hardware evolves, so you would also kind of have to consider the maintenance costs, licensing, these kinds of things. This is an example which I've shown you before, which was done with Amira at that point in time. So basically what you would do is you would load in the data about that particular geographic area, so Mediterranean here, Genoa here, and once you have that, you would overlay it with the data from the simulation, which shows then where the flooding is taking place. So this is the DREAM project, which was studying this flooding examples. Yeah? So here we really had something in reality which was overlaid with something which is also real, but came out from the visualization, from the simulation. And then we could compare whether it fits to what we see in reality. And the visualization was critical because the guys simulating the flooding, they work with the formulas, just as you are mostly working. But those people who take care of the flooding, who have to do the evacuations, they understand maps and geography. So they need to see what happens. It doesn't help for them if they see a formula. They want to see what would it look like in reality, which streets will be flooded. Take the second example. So a different area, this one is from engineering. It was actually done at the University Stuttgart, at the HLRS, which is one of the other national HPC centers. And they again did it in order to have an extensible modular software environment. You would again add your own stuff there. It also has a collaborative factor, which comes in because more people want to discuss what is going on. And again here, support for stereoscopic rendering. And this one used to be a product, they made it open source for whatever reason. But here you can do even more manipulation, even more changes to the code. And again, we used it for one of the projects. And you see this is not even much different from the previous project. But basically at that point in time, we had the Climax project. They came to us and said, we want to see the effects of climate changes. And again, you see simulation data over a real existing landflow. So we put on something that was artificial created, interesting enough, and don't ask, that's a political reason. It's between Bavaria and Quebec. So yeah, political. I heard that one of the persons from the ministry likes to go to Canada for vacation. So that was one of the political incorrect jokes. No? Now, the point is, whatever data you have here, you want to couple the simulation data with something real, and then again, you want to make it visible. People understand it more easily. And this is really like going there. We had the data, we just wanted to stick it in. It didn't take long to produce that. And now if anybody in the room can tell me what you see, you're better than me, actually. Yeah? So I need even the scientist there to explain what's going on. Now, there's more tools there, and I stopped with the examples here. One of the most commonly used is ParaView, which comes out from the US DOE labs. And that's again, it's a similar tool that was actually done just out in the need for it. Yeah? So people were simulating stuff, they wanted to visualize it, they wanted to come to a point where they could work with it. And interesting enough, the point here is it works with very large data sets. Question there is, how can you make a tool that scales well on visualization hardware? So you have some limitations, and you have seen many of them already in the examples. The standard software tools can often not fulfill what you want. So sometimes you really have to think about, what is the input data? Is that a standard format that I could read in? What is the file format? What is the size of the data? Can you actually load it into the system? How would you pre-process the data? You need to filter something. You have a filtering stage. You don't want to show everything. You want to see just certain aspects of the data. It's highly optimized, and you would also, as I said, adapt it to what the user needs. So in these cases, it's probably best if you just start with a framework and then build your own stuff, which is VR tools is one example. And we're using other things like the open scene graph, where you really construct your own visualization for a specific purpose, and then the person can use that. Here is an example that is, you have seen that before, that's Hans-Peter Bunge from the geophysics domain. I've mentioned that before. The interesting part here is 607 gigabytes of data, and that's the small model. So you need to load that in, and you would build your visualization on that. Right now we're working on a model that has 13 terabytes of data. So even that alone, this is the simulation result. It's a huge simulation. We want to visualize it. We need to kind of focus on the important parts, and the important parts is 13 terabytes. There is no software tool simply to do that. We have to optimize ourselves. And that's what one member of the team is actually doing, trying to develop that. So what we kind of do here is we have task forces that go in. So like Ruben is here for Nomad, working on visualization of your data. We have different people on different projects. And the idea is really you get one of these persons, they work together, and then you produce something like this here. And this example here is also interesting in a sense that once we develop that, it is really used on a daily basis by the scientists. So the geophysics people reserve the room, they book the room, they're in there half a day, full day, they study the data, they correct their model, they see mistakes which they found out between the simulated data and the actual observed data, and in the end the model gets better and better and better, and then you can study what's actually going on there. Other examples, and I'll skip that because I understand that Ruben was showing some stuff. I mentioned that already. It's also a customly built tool specific for that purpose, and I think it has also shown during the review that it was useful to do it this way. Now we go further with the rooms. You see some pictures of the rooms here. So we also want to kind of study what the new technology could bring us. And you have these cardboard displays, which I like the idea just to bring them and hand them out. But of course you would also might want to see it in a room or something, and with different possibilities all connected to that particular project. So kind of coming to an intermediate summary. I hope I was able to show you some examples and to give you some ideas that this is a challenging topic. I'll skip the mathematics. I'll just focus on getting the output, the rendering. Whatever is the best way depends on what you want to do. So a clear idea on what you want to visualize helps. And of course you have all the constraints that you have to live with. So the interactivity is clearly a constraint. That means that you have to produce a certain amount of pictures per second. That comes back to the important part, the human factor. And you should always think that you are living in a filter bubble. Your filter bubble is material sciences. You know how this looks. You know how this looks if you take a closer look. Yeah? But maybe somebody else does not. So if you want to show something, visualization can help you. But you also need to kind of step out to get to a point where other people understand that. And I was taking politicians as example. It works for everything. In fact, I believe that visualization is also an important part if you have to justify the government money that you get. Because most people at least get an idea what you're dealing with. And again, your example with in Nomad, with the materials and how this actually, what happens on the material is a good example of that. So I skipped the point about the pre-processing, because that in itself is a large task. What do you get? How do you get out the data? How do you, again, starting from the precision that you have in the data to the granularity of the display. Even a 4K display has a limited number of discrete pixels. And the mapping there also needs to make sure that you get something there. So whatever you do, this large data set, even if it's 13 terabyte, you wouldn't see it on the display because you see only parts of that, of course, there. So you have some more things to do also in the pre-processing step. And with the hardware limitations, we mentioned that with the terabytes, but of course you have more things. The simulations that we're talking about take days. If you want to interact with the simulation while it's running, well, we had that, you know. You were changing something. Even when we did the gearboxes here, you were changing something, and then you were able to go for a cigarette, or these days you go for a glass of water probably, and you come back, and then it was actually visible. We still have these limitations. because while hardware is improving, the data is also increasing. And we talked about the tsunami of data coming in. Yeah? At our center, we have 200 petabytes of storage available for all the stuff. We're using only 65 petabytes of the data. But the problem is people, groups like you, increase the data. We are actually doubling every 14 months. So we know that 14 months from now, there will be twice as much data to store. And we know also that 28 months from now, we won't have enough capacities to store all the data. And the same tsunami needs to be considered when you're doing visualization. So it comes to a point where graphics hardware needs to improve, and actually we are benefiting from all this entertainment stuff. When they are improving the graphics cards for the games, they're also kind of addressing some points in what we are doing. I mentioned the interactivity in a number of ways already, how you could kind of put the user in, and then just as a summary, you can fit all these things together. Now, I'm coming to the end, but I wouldn't want to skip a little explanation, why are we doing this? So what you see here is the Leibniz Supercomputing Center. So this is the core part, 10,000 square meters of hardware equipment. This is where all the simulation machine stands, and SuperMOOC is actually on the top floor here. And you see some of the cooling engines on the rooftop for SuperMOOC. So SuperMOOC, I take one number. The electricity consumption per hour is 1,000 euro. So just for electricity, we need 1,000 euro, and of course you need to cool that. That's why this stuff is up here. Now, there is a small, this is the twin cube. There's a small cube here in the background. This is the visualization center. And it has actually only one room. That room is 12 by 12 by 12 meters. And we can only use a small fraction of the room because what we wanted to install is these two devices. We have a large power wall, which is 6 meters by 315, and we have a 5-sided cave. And we wanted to do that in a way that a person in front of the picture does not obstruct the picture, doesn't make any shadows or hide anything you want to see. So what we wanted to do is we wanted to put the projectors on the backside. You see here 2 projectors. These 2 projectors go via mirror and then produce the picture on the rooftop. So what we use here is we have only this small area, which is about 1/3 of the room, left for where the humans are standing. The rest we need for things like trivial things, like the distance between the projector and the wall you want to project on. And the projector here is somewhere in the back, up there. It's also, you see the distance there. The point here that we have is we are not researching graphics. We are a service provider. So we have exactly that problem where we have to interact with users who want to visualize, who want to use the infrastructure. That's an easy part. You can book the room. But also who want to put their own data there. So we have to help them with the preparation of data sets. And those people working with Ruben, again, as the last time to mention him, they know how much work it is. You provide data sets that you want to visualize, and you need to explain what you want to see, these kinds of things. So the service is the infrastructure itself, but also the human service providing help with the visualization. And for us, the research aspect is also interesting because we use people like the people in the room also to drive us forward. Because if your data grows, we need to think about new approaches. If your requirements change, we need to think about how we could incorporate that. So research in our case means how to advance the services that we have here. One of the examples we are doing is we are not trying to install an LED wall, which should then also provide 3D visualization. And it will, of course, be also interesting if that works with your application. And with that one, I thank you for your attention. I think that was the time that I was allowed to speak.
Over perfect.